about the training for those who are continuing. Right now we have Levy, is a computer science PhD student at Mosik's lab in the Hebrew University. His current research is on Exascale operating systems, runtime systems for heterogeneous systems, and libraries for massively parallel computing. Previously, he worked on fair share and economic grid scheduling, transparently running OpenCL over a cluster, and OpenMP cluster extensions. Eli is an experienced system programmer who worked for 10 years on developing tools for efficiently using cluster and grid systems. Okay, half hour? Go ahead, it's all yours.
Okay, thanks for introducing me. Like I said, we're working I'm working as a research student at the Mosik's lab at Hebrew University. And I'm going to describe our work as part of the FFMK project, which is a project together with a few universities from Europe about creating an Exascale operating system. So first of all, we saw that everyone talking about Exascale, but what is Exascale? So like the person from Intel said, Exascale is a large amount of CPUs. A very important part of the challenge of hardware for Exascale is having low power consumptions and not going to the exponential power consumption that was so far with current hardware. Current top CPUs or GPUs of E or processors like that are around 1 teraflops. That means that in Exascale system we'll have like 1 million CPUs. So that's the amount of CPUs we need to handle in an operating system that should run on Exascale. The project in a nutshell, the challenges include, of course, scaling. We need to scale, programs need to scale both in network and runtime over a large amount of processes. Failures. We expect constant failures. I mean, the more CPUs you have, the more hardware you have, the more chance you have for failures. Load imbalances. We look at mainly at MPI-based programs. We look mainly on MPI-based programs. And as you know, MPI programs need to be synchronized, and it might very well be that one part of the MPI program finishes a bit faster than the others, and we need to someone deal with it so we won't delay everything else. Heat and power management, that's power and heat is a huge problem when it comes to this scale of computing. Information collection, we need to collect information about all the nodes in the cluster. When there's 1 million of them, it's also a problem. We go in the direction of self-organizing platforms and application. The platform is supposed to have autonomous parts that can manage themselves. This way it can scale better and, of course, work with less overhead. This sounds like a pretty crazy project when we first look at it. What saved us from really not knowing what to do is the fact that it's based on 4 technologies that were already mature and are being used in semi-production environment. L4 is a well-known microkernel. It's used on phones these days and on computers and on many other hardware. ExtremeFS is an open source system that is fault tolerant, and it knows how to handle faults during the nodes and auto recovery. Those 2 groups are also working with us, the ones who developed those 2 things. Mosik's is what we developed in our lab, is a cluster operating system that supports process migration, information dissemination, scheduling, and other things like that. And of course, MPI, which is a very well-known technology that people now use to run over clusters. So what are the hardware assumptions that we need for this kind of operating system? First one is high failure rate. Already today, there are a lot of failures in big computers, at least 1 or 2 a day, and if you have a job that runs on many cores, the more cores that it runs on, the more chance that it has that it will meet a failure somewhere in the middle. Another problem is that not all cores can work together. I mean, the more cores you use, the more power and heat problems you have. So we want to balance the amount of power and heat that's being used by certain parts of the system. What we do assume is that you have low power storage, such as flash memory or something like that, for checkpoint the state of each node, because checkpointing the state of all the nodes together is another very huge problem. So the usage is indeed many cores, many nodes with computer services nodes. Targeted application that we look at is MPI based. And you have a stage of communication, usually in the beginning. Then you have a stage of computation that all the nodes do the computation that is needed. And in the end, there is another stage of computation. And this is going in circles and until the job finishes. Here it's drawn all nice and stuff, but we need to remember that there can be a failure in the middle and one of the nodes can fall, and there can be a node that takes longer than others, and somehow the operating system will need to manage that. So the state of the art today is static assignment. First of all, we have a very smart static assignment on the computer-wide or system-wide, and that assigns the number of nodes that are needed by the job, or at least the number of nodes that the job thinks that it will need now. And then the job itself manages the node that it was given. We want to go in Exascale towards dynamic applications. Since we know that application programmers don't always know how much the computation will take and how many nodes they would need. And sometimes the system is now in high load and it can't get many CPUs, but then we have more free nodes and we want to be able to use them. So here, like we see now, one application, the green application, became smaller. It discovered that it needs less nodes, so it profit the nodes that it didn't need. On the other hand, the other application took more nodes that according to computation. We also see that it moved aside, could be from for heat or load balancing purposes. Now we see that there was a failure in one of the nodes. This caused a delay. You see at the long line, we see that there was a delay in one of the applications. The application can split itself, this node that took longer, to 2 nodes or something like that, and then it will be able to return back to the according to the other nodes, the time table. So the system architecture. The red parts that you see, or purple, they are the ones in L4. L4, as I said, is a microkernel that runs above the different compute cores. The main trick in here to prevent rewriting the whole applications again is that it can run Linux emulation that can handle Linux system calls. What we see is that the MPI and the file system is actually split between the 2 layers. Part of the MPI, the one that needs to be real-time and fast, which is mainly the communication layer, is done in L4 directly. And the actual MPI library or file system API is done in the Linux layer. This way, it gives a balance between rewriting the whole system and between getting good performance. We also see that there is a Mosix module which will run above the Linux layer, and it will tell the applications how to manage themselves and pass the information around the cluster. Okay. So our group in Mosix, we look mainly at the information collection problem at the moment. Of course, before you start looking at scheduling, you need to know how to collect the information, so you will have all the information at hand when you need to do the scheduling. So given 1 million nodes, we have each node needs to send one message each unit of time. The message needs to contain the information that is needed for load balancing, things like how hot the temperature, free memory, load, availability, if the node is up or not, and all this needs to be circled around the cluster. We have one master computer, which is the one who is doing the global scheduling and monitoring of the system. It also does the job allocation. For example, these days Slarm is very commonly used for that, or Oracle Grid, or one of those systems. This node is usually hard node, and it's mirrored for fault tolerance and stuff like that. The problems that we need to face is how to collect the fresh information without overloading the master computer with all those messages and information. So we want to use distributed bulletin board. Information is circled continuously. We need to watch that the unit of time that we circle the information, of course, is not too small in order not to overload the network. We need to notice as part of the events, like scheduling is done by the master, and the master is node has the information about them. It needs to circulate to the rest of the nodes. On the other hand, there are all kind of events like load balancing or heat that are triggered by the nodes in the cluster and not the master. The purpose is that we work all the time, and when someone needs the information, it's check on the local node, and it gets the fresh information that the node has. So possible algorithm, of course, is first of all is to use centralized algorithm. Each unit of time, each computer sends the information to the master. The drawback of this kind of algorithm is very clear. You need to handle 1 million messages every time units. It can be very, very time-consuming and and have a lot of networking overload. It does work for medium-sized clusters. That's what we use these days. And when you look at clusters until like 1,000 nodes, it works fine. Another common solution is using a tree. Each node sends it to one above it in the tree. Each tree node has a few leaves, and this way we reduce the amount of messages. This has two problems. One is fault tolerance. If one of the nodes in the middle falls, then it's really hard to replace it. There are all kind of complicated algorithm for dynamic trees that's supposed to manage that, but it's not so easy. And the other thing is that you have O of log messages and unit of time that needed to get to the master. So what we use is something known as randomized gossip. We use a distributed bulletin board. Each node keeps one vector with the information about what it knows. And one time each steps, the node sends one other messages to randomly chosen node. This is called a window. I mean, it sends the message about itself and a few other nodes that it has fresh information about. The node that received the message merges the window to its local vector. I see that the animation is not working so well. It's supposed to be animation here that you see white lines sending one to another. Maybe I'll show it like that then. Okay. So here is an example to how the gossip algorithm now works on Mosix. And we see that each unit of time will keep bothering me. we see that each unit of time it updates the local vector. Don't know why it does that. Each unit of time it updates the local vector, and it sends. We see that we have the name of the vector, which is A, B, C. The name of the node, sorry, which is A, B, C, D, E, and all those name of vectors of nodes. And the number next to it is the age of the time. I mean, the local node is A, for example, so the information age is 0. But for example, from B, didn't get any information, new information for the last 12 time units. We define some T, which is a constant that tells you how old information we send. So for example, if T equals 5, then we remove all the entries that are above 5, and we just send information about A, C, and D. And of course, this information is sent to one other randomly selected node. This node, upon receiving the window, we see that it received the window. First of all, it updates the time. It added one to each of the ages. So A is now 1 and C is 3. And it merges the new times according to how new the information is. So for example, for A, it took the information because it's newer than the one it has. Also for C. But for D, it has newer information, so it didn't update the vector. Okay, so this is how it works now on small clusters or medium-sized clusters. But when we go to 1 million nodes, we need to be more scalable. For that, we use a two-layer gossip algorithm. We divide the compute nodes into colonies that information is passed between them. This division of colonies probably should use some optimization criteria such as networking proximity or something like that to make the network efficient. This is we now starting to run tests, and we saw that, for example, on Blue Gene, it's very important to reduce the amount of hops that is needed to get to between the nodes. Colony node exchange the information, and also that is needed for what they call local management. Local management is load balancing that is done inside the colony. This can be done, for example, for heat balance. No need to go through all the system. We can just make sure that we keep a few spare nodes on each colony, and then you can do minor adjustments inside the colony without making noise all over the system. And of course, any client applications that need up-to-date information can ask about the colony, can ask each node in the colony. But if you need information about all the cluster, then you need to ask the master. The master collects in the information from a few nodes in each colony. It asks 1 or 2 nodes per colony is usually enough. And it provides the scheduler or any other client that needs to have global information with this information. Okay, as then, of course, nothing comes for free. Like any other algorithm, it has a trade-off. And the different parameters that you can give to this algorithm, like T or the rate or stuff like that, is of course dependent on which part of the trade-off you want. So for example, the colony size, the bigger the colony is, the less fresh the information is, because you need to pass it between more nodes. But you have more global information, and you can get more spare nodes, and you can do more adjustments than if you have a small colony. The colony topology, if you have spread colonies and you maybe have more tolerance for faults and stuff like that. But for example, the node is not focused, the information. Or dissemination rate. If you pass a lot of information, you have high networking overload, but you have fresher information. Another threshold is that if you make the value t higher, t is the value of how old the information that we are willing to send, then we have bigger window size. But of course, we also get for that we have a lower average age that each node of each vector on each node for more information that we need to send. Results, which are work in progress. We see that now the average age of the vector on the nodes. And this is an average of the average age actually on the nodes. Our work is special in that it's both theoretical. You see the approximation lines, which is a mathematical analysis of how this algorithm should behave. We have a simulation run that we use to simulate the run on big clusters. And we also have an emulation that we hopefully will get until 2K in the end, that is run now on Blue Gene computers. We can see that the results are very, very close. I mean, we see that the approximation and simulation are very close to the emulation, which the emulation is actually running the real algorithm. The only thing that is emulated is that no one is actually using the information, but it's actually the real algorithm. And so, for example, you can see now that if you make t higher, then at some point it stops becoming better. For example, if we can see that in 7 in colony of 128 computers. And the reason for that is that at some point we started to send the whole vector of that we have, and then it can get better than that. So, for example, in 7 we get for like window size already of 127 entries, which is almost the whole cluster, the whole colony. The same goes for bigger sizes. Only in 8K it starts at in average age of 10. You get to only percentage of the cluster and not the whole cluster. We also, the advantage of having an approximation is that the simulation also gets until a certain size and can't get higher than that. So we put the approximation just to show you that you can go up forever, and at some point the information that you get is ridiculously old and not useful. So at the moment, from our experience, what we saw is that using a 1K colony with around 5 or 6 T size gives the best balance inside the. This is inside the colony. Now we'll see in the master computer. Into the master computer, we always send the whole vector to the master computer. I mean, they send a window between each node in the colony, but the master gets the whole vector that the node has. We see that the average is better than the ones inside the colony, like you expect. Of course, in the higher price that we send the whole vector and more information to the master, but since it's only for one computer and it's not so much, then we can allow the self to us. And again, we see that the results are very close between the approximation, emulation, and simulation. So yes, the sweet point looks somewhere in 1K and 5 or 6 T from my experience. Since this is work in progress that we do just now, we're also planning to run to see how this is affecting the program that actually run on the computer. So far, we saw that using time units which are around 1 second, they almost have no effect over the program that we're running and gives very good results. Okay, questions? Yes.
General question regarding these big large clusters.
Yeah.
Basically, this big cluster deal with failures and also with the ability to move large chunks of data to the nodes to operate on them. However, there is another technology, not quite like HPC, called the Hadoop ecosystem, also open source, that deal with these two issues, deal with failures and deal with data movement. Is there any way to combine?
First of all, we're in this project, we're going around for operating system. So, of course, Hadoop is a program and might very well work on this operating system. Today in HPC, MPI is still much more common. That's why we took it as a use case. Hadoop is also a very interesting use case, but it's more for large data and less for HPC.
That's not my question. Is there a way to get both, the best of both worlds together?
Well, we didn't look into that yet, but it's certainly on our radar to look also on Hadoop. It's a very famous framework, and it's very interesting. Yes?
How would the numbers compare to use of, you said that it's not useful to use a tree in that way, but if I would use a flat tree, and for me this is some kind of a flat tree, I would compare it to a normal flat tree if I use a flat tree.
The main problem with a tree is that it's not fault tolerance. Yeah, if you use a flat tree, it's not really a tree. You just use the two level. But a tree usually, when they use tree, is using more than that, and then you have a real problem with fault tolerance. Also, if you use tree here, then the nodes, you need still to circle the nodes among the clusters in the computers in the colony, and that you don't have in a tree.
There's also so much times to incorporate fault tolerance in MPI, right?
Yes, part of the project is to manage fault tolerance in MPI and to manage fault tolerance with the operating system.
So it would be possible to use flat tree.
Yeah, but flat tree doesn't give you the information between the nodes. Flat tree only gives you the information to the master computer. It doesn't enable you to have local management. If you have more than if you have a few layers of the tree, then you can have you can say, okay, we take this layer and each one of them is take care of part of the cluster. But if you have only flat trees, then the master needs to handle everything together, and you don't have information between the nodes.
Okay, thank you.